Okay, so the random walk. Okay, this is a really beautiful application of independence and probability in general. So let me tell you what the scenarios that we're going to analyze. So there's a street, there's a bar, the drunk walks out of the bar, forgot, where home is home left or right? So, and also the guy's drunk and has no short-term memory, nothing. Okay, so the guy, walks left, and then takes a moment to breathe and then walks left or right, or when he comes out of the bar, he could walk right. So basically the drunk walks left or right randomly, okay, with equal probability to go left or right, and he has no memory. Okay, and, in one direction is the jail. If he gets to jail and is that drunk, he's going to be put in jail for the night. And the other direction is home. If he gets to home, he sleeps well. Okay? And so, this is an example of a random walker. The drunk is walking around randomly. You can think about it, you walk out of a bar, you don't know whether your car is left or right, so you might randomly walk around looking for the car. So the question is, what are the chances that you will find your car? What are the chances that this drunk makes it home? So here's the scenario. Okay, so there's a bar, and the bar is at some position, and then, let's just make a simple example. So here's home. Okay, so here's home. And let me try to draw home. This is my image of the drunk's home, and here's the jail. Okay, so the jail looks something like this. Okay. Now, the drunk starts here and can walk right or left, okay, with equal probability, 1/2, 1/2. Okay, and let's try to see what can happen. So what are the possible sequences for moves of the drunk, that can happen. So if the drunk moves left, he's at home, and that's the end. He gets into bed and sleeps. So L. Okay, and what are the chances of that? L is 1/2. Okay. Now he could move right. Okay, he could move right. In which case he's in jail. Okay, and again, the whole process stops and he sleeps in jail for the night. And because of independence, now this is where the independence comes in, because each step is independent, the probability to walk right is 1/2, and the probability to walk right again is 1/2. So we have 1/2 times 1/2 because of independence. You multiply probability, so this is 1/2 squared. What else can happen? Instead of going right, he can go right, left. Okay, and now he's back to the bar, and from here he can either go left, okay, in which case it ends, so right, left, okay, and the probability of this is 1/2 cubed, okay, or he can go right, left, right, so right, left, now he can go right, okay, in which case he's in jail, so that's 1/2 to the 4th, or he can go right, left, so right, left, and he's back at the bar. Then the probability of this is, the chances of this is 1/2. Okay, but now if he's back at the bar, he can go either left, okay, or he can go right, left, right. That's another way to end. Okay, so this would be 1/2 to the 5, and this would be 1/2 to the 6. Or he can go right, left. Okay, and now he's back at the bar, and he can go left, or right, left, right. That's another way to end this random walk. Okay, so this would be 1/2 to the 7, and this would be 1/2 to the 9, and so on. These are the possible outcomes for the drunk. Okay. Now we're interested in the probability to make it home, okay, and so what are the chances of making it home? The chances of making it home are here, 1/2. Okay, that's an outcome where he makes it home. Another outcome where he makes it home is right, left, so he makes it home left, right, left, so right, left, he makes it home. Okay, right, left, so we can call that right, left, squared left, and he makes it home. Right, left, so right, left, cubed left. Okay, and in general, any number of right, left moves to some power k, followed by left, brings him home. And those are all the sequences that bring him home. Now let's see what are the probabilities of each of these outcomes. And now we can use independence. This is 1/2, this is 1/2 cubed. This is, there are 5 here, so this is 1/2 to the 5. And this is 1/2 to the 7. This is 1/2 to the 2k plus 1. Okay, and we see that, the probability to make it home, okay, now these are the outcomes where he makes it home, so that defines the event of interest. The probability to make it home is exactly equal to 1/2 plus 1/2 cubed plus 1/2 to the 5 plus 1/2 to the 7 plus and so on. Okay, so this is the infinite geometric progression again. This is equal to 1/2. So the first term divided by 1 minus the common ratio. The common ratio is 1/4. So 1/2 over 1 minus 1/4, which is equal to 1/2 over 3/4, which is equal to 2/3. So not bad. The drunk will sleep at home. The chances the drunk sleeps at home are approximately 2/3 or 67%, 33% chance of being at jail. Now let me show you another way to get this same answer, but using the law of total probability. Okay, so law of total probability. Interesting. Okay, so the law of total probability. We can say that, well, the probability to make it home. Okay. Now the law of total probability says break it into cases. There are 3 cases. Okay, either he moves right, so it's the probability to make it home, given that he moves. Either he moves left, so the probability to make it home, given that he moves left. Okay, weighted by the probability to move left. Okay, so this is what the law of total probability says. Plus the probability to make it home. Okay, now the walk can start with either right or right-left. So probability to make it home, given that he starts off right, times the probability to move right, plus the probability to make it home, given that he starts his walk right-left, times the probability to make it, times the probability to start right-left. Okay, and this is what the law of total probability says. Break it into cases. There are 3 cases for how he can start off his walk. Either he moves left, okay, that's one case, or he moves right, or right-left. There are no other cases. So you compute these conditional probabilities, weight by the chances of each of the cases. Okay, now comes the interesting part. The probability to make it home, given that he moved left, is 1, because he's already at home. So this is 1. Okay, the probability to make it home, given he moved right, is 0, because he's in jail. So this is 0. Right. And the probability to make it home, given that he moved right-left, okay, that's the interesting case. If he moved right-left, he's back at the bar. So it's like this process is restarting. The random walk is restarting. And the probability to make it home, if he starts right-left, is exactly the probability to make it home that we're trying to compute. Because the probability to make it home that we're trying to compute is exactly the probability to make it home if you're at the bar. So this is the probability to make it home that we're trying to compute. Okay. So this is going to equal 1 times the probability to move left. That's a half. So it's 1 times a half plus 0 times whatever is 0 plus the probability to make it home times the probability to move right-left. That's a half times a half, independence. So that's a fourth. Okay. And so what we have is that the probability to make it home is equal to 1/2 plus 1/4 times the probability to make it home. Okay. And this is usually the case when you try to analyze such infinite processes that could go on forever, because he could keep on going RL, right, left. He could keep on going forever. You get an equation for the quantity you're trying to compute, the probability to make it home, in terms of itself, which you have to solve. So we take this to the other side, probability to make it home times 1 minus 1/4 is equal to 1/2, or the probability to make it home is equal to 1/2 over 1 minus 1/4, exactly what we got before. This is 2/3. Okay. That's, in some sense, much simpler, because you don't have to analyze this infinite set of outcomes, and we don't know if we did this correctly, but here, everything is nice and clean. Simple, 2/3, correct, bam. Okay. Now, I'm going to show you an application of the law of of the random walk to gambler's ruin. Okay, so gambler's ruin. Okay, so this is an application of the random walk, almost direct application. Gambler's ruin. So here's what's going on. You're a gambler. Okay, you walk into a casino. You have $2. So you're a poor gambler like me. You only have $2. Okay, and you're going to play a game. Okay, and this game obviously favors the house, but at each step you're going to bet $1, and you can either lose the $1, which means you drop in wealth by $1, or you can win an additional $1 and you increase your wealth by $1. So you start with $2. Okay, and each time you play the game, you can either drop in wealth from 2 to 1. You can increase in wealth from 2 to 3. Okay, that's the ideal situation where you increase in wealth. Okay, and if you're at $1, you can bet your $1. You can either lose. So you have 0, and now you're clearly unhappy. Okay, and we say that you've been ruined. Okay, so that's ruined. On the other hand, if you have $2 and you win, you move up to $3. You bet your dollar again, and if you win, you go up to $4. Now, at some point, you have to decide that you're going to leave the casino. You can't stay here forever. Okay, so obviously, if you get ruined, you have to leave. And we will say that your goal is to double your money. So if you get to $4, you win, you're happy, you leave. Okay, so you're happy, you win, you leave. So in some sense, you're a very disciplined gambler. Okay. Now, of course, real gamblers, once they get to this point, they think they're on a streak, and so let's keep going, let's try to double again. Okay, we'll see that that's a disaster. Okay, now let me show you what's going on. Okay, now clearly, this game is going to favor the house. So, let's say you start with your $2, and essentially what's going on, you either move left or right at each step, okay, with some probability. So let's say that you move left with probability Q, and right with probability P. Okay. Now, in the random walk, the drunk, it was truly random. He walked left or right randomly and independently with probability 1/2. But because this game favors the house, Q will usually be bigger than P. So you're more likely to lose than to win. Okay, so let's set Q equals to 0.6 and P equals to 0.4, just as an example. Okay. Now, the obvious question that we want to know is, what are your chances of winning? What are your chances of doubling up before you get ruined? So what is the probability to win? Or equivalently, what is the probability to lose? To ruin. Okay, now if you think about it, this is exactly the random walk problem, where you can think of ruin as the equivalent of jail and doubling up as the equivalent of home. And we would like to know, if you keep playing this game until you either get ruined or you win, until you double up, what are your chances of reaching, your double up state before you reach the ruined state? Okay, same question here. What are the chances of reaching home before you reach the jail? Okay. And we can analyze in exactly the same way. You can build up the sequences that lead you to ruin or the sequences that lead you to doubling up and add up the probabilities, and it's complicated and tedious. Or you can take the law of total probability approach, and in the text, we analyze the general gambler's ruin problem, okay, where you can imagine that you have some number of dollars and your goal is some higher number of dollars, and you'd like to know what are the chances that you reach your goal before you get ruined. And we can even do this whole analysis for general Q and P. Okay, Q plus P must equal 1. So if you want to see that analysis, read the text. But a very good exercise for you is, for this specific scenario, compute your chances to win, or equivalently compute your chances of ruin, and take 1 minus that, you get your chances to win. I'll just tell you the answer. Okay? We use exactly the same techniques that we used for this smaller example of random walk. This is another random walk, a little bit more complicated because it's got more places to go, and a little more complicated because it's not half. It's PQ. P is 0.4, Q is 0.6. Okay? But your probability, your chances of ruin are approximately 69%. Approximately equal to 69%. Now, that's not so surprising. And that's basically what gives the house these odds, right? The house has got better odds than you. And so it's more likely that you get ruined. So you might try to defeat this strategy by saying, I'm going to walk into the casino with more money. So let's say you start with $3. Start with $3. You might think, well, so now my game is as follows. I'm going to do the same thing. I'm starting with $3, and I'm going to play until I either get ruined or double up to 6. What are my chances of ruin? Chances of ruin are equal to approximately 77%. Wow! Your chances of ruin went up if you start with more money. So let's see what happens if you started with $10. So you'll play either till you get ruined or till you double up to 20. Start with $10. Chances of ruin are approximately 98%. Wow! So in this game, trying to double up with $10, okay, you will get ruined 98% of the time. It's truly a gambler's ruin. In fact, when you play this kind of... Okay, now this was for these specific odds, but you can do it for general odds. In fact, when you play this, gambler's ruin game, okay, the more money you start with, the richer you are. The richer you are, so the richer you are, the more likely you are to get ruined. The more likely to get ruined. Wow. It's truly a gambler's ruin. The richer you are, the more likely to get ruined. Okay. So you want to avoid the gambler's ruin. Avoid this kind of a scenario. And you might think, what are other better strategies which give you a better chance of winning as you get richer? Okay, so that's an interesting problem. It all falls within this realm of random walks. Okay, so that's the end of today's lecture. Let's just recap where we are so far. We have mechanical ways of computing probabilities, which are interpreted as how often does the event occur. Then we know how to update probabilities with new information. That's conditional probability. And today we studied how probability gets easier to compute when you can assume independence. Okay, so be on the lookout for independence wherever you are trying to analyze probabilities. It makes computing probabilities much easier because you compute the probability of an AND by multiplying probabilities. Okay, and with that, I'm checking out. Till next time. See you next time.